All right. Good evening, Math 261 students. Welcome back. This is our fifth meeting together. Yeah, that sounds right. Fifth meeting. Reminder of a couple due dates, 1.4 and well, that's already passed. 1.6 is going to be due on the 14th. 1.7 and 1.8, which we'll knock out today, will be due on the 21st. We're also going to make some progress into chapter 2 today, but because of the test that I'm going to talk about for a minute or two, being next week, I'm going to hold off on any due dates for chapter 2 for now, just to be nice, so you can focus on chapter 1. But like I said, we will finish chapter 1 material tonight, about halfway through the evening, something like that. And yeah, we're going to go right into chapter 2. So anyways, your first test is going to be in MyMathLab. Now, while I am going to eventually do proctored exams, so where you'll have to have like a video camera on you while you take your test in MyMathLab, your cell phone would be fine, webcam, whatever. This first one will not be. Sorry, my dog is bugging me right now. I'm trying to get him away, and he's really distracted me. So your first test is going to be available on the 21st, 22nd, and 23rd. So that's going to be that Monday through Wednesday of next week. So you have 3 available days to take it. We will still have class on the 21st, just so you know. We will still have class on the 21st. So if you do not have any time to take it on the 21st because of class, then you can take it on the 22nd or 23rd. And I know most people tend to wait till the last day to take it, but please make sure that you will be available to take it on the 23rd. Don't wait until 10 p.m. on the 23rd to start it, and then you might have technology issues and oh no. So your test is going to be due by 11:59 p.m. on the 23rd. So at midnight, that's it. There's no more submissions. You will have to show your work and submit in Canvas within 15 minutes of finishing. So put your name on your work, show your work. You can write it, you can type it, whatever. You can take a picture of it. You can send me a PDF. It doesn't really matter. I'll take all kinds of files. You can take multiple pictures, multiple files, and send them. But the 15-minute deadline is super serious. This is to make sure that there's no funny business going on. And this is a calculus test, so you're going to have to show some work here and there. You might not have to show work on every problem, but if you don't submit your work, I do reserve the right to give you a 0 because I might suspect funny business. The test itself will be 20 questions. You'll have 2 hours to take it. You're not allowed to use notes, books, or calculators. Again, there will be a calculator-based test later, but for now, we're sticking to no calculators. There is a review available in MyMathLab. So when you go in MyMathLab, the test, when it's available, will be the very top assignment. The review for chapter 1 is immediately under the 1.8 homework. The review will be comparable to the test itself. So please, please, please do the review. The review is not going to be part of your grade. It'll tell you whether you got a 50, an 80, 100 on it or whatever, but it's not going to be part of your calculated grade. So yeah, some students skip the review and still do okay, but most students that make good grades are the ones that have been doing the homeworks and do the review. And again, the review will give you a really good idea of what to focus on for the test itself. And it's just like the homeworks where you have the view an example and help me solve this for most of the problems. So when you go in Canvas, we don't have very much in our Canvas shell, just a couple of review documents. When the test is available, you will see a link that'll say submit test 1 work here, and that's where you'll click to then submit your work. It's pretty easy to upload a file there. It shouldn't be any, there shouldn't be any complications. And yes, like we said, the review is just like the homework assignments. It will give you answers to things that you mess up, and you can go back and try again and try again and try again, whether you get it right or wrong. So again, a really good opportunity. All right, so with that being said, let's go ahead and dive back into the last little bit of chapter 1 we got to do in 1.8. And, or did we have some 1.7 left? I actually just forgot all of a sudden because I was planning my my notes for the last half of the class. I did the first half yesterday. But yeah, so let's go ahead and pick up where we left off. We were in the middle of an example, I believe, actually. Yes. Not in the middle of an example, we just finished one. We're going to be doing the quotient rule next, 1.7. That's right. So we have a little bit of this little video left, about 20 minutes. Then we'll start another one. We'll have a break at about the hour and 20-minute mark per usual, about a 7, 8, 9-minute break. and then we will continue where we left off after that.
So that problem had a decent amount of complexity to it, but I still think chaining a chain is more complex. Opinions will vary. Now again, the problems that I do in lecture, these are comparable to what you'd expect to see on the test, and I'm trying to make sure that the homework problems line up pretty well as well. And by the way, in this homework, if you already did a couple problems, one of you is a real go-getter at least. The last like 5 or 6 problems I gave as freebies because they were kind of extended concepts, more complicated, whatever, you know. All right, so one more of these. We did the product in the chain, now let's do the quotient in the chain. So f of x equals, and this is x plus 1 over x minus 1 cubed. Now, you could have a product that needs to be chained, or you could have a chain that needs to have a product rule done. The last one was one way. It could have been done the other way. This is kind of like the other way, where the quotient is inside of the chain rule. Last time, the chain rule was not inside of the product. It was part of one of the factors. What I'm saying is, you could have also had a problem that was something like x plus 3 times x minus 7, and then this whole thing is raised to the, I don't know, 10th power. That would be chaining a product instead of a product and chain. Okay. So this is a quotient rule. One more reminder for the quotient rule. If you had f over g, instead of calling them first and second, it goes the second times the derivative of the first minus the first times the derivative of the second, all over the second squared. All right, so this is just one big inside and outside, so we're going to chain this at first. We would call the inside the x plus 1 over the x minus 1, and that makes the outside everything cubed. So red x representing the inside, and then cubed. So then remember, if you need to make a note of this, your little red x really represents the x plus 1 over x minus 1. Make sure you're not writing that x in the derivative in the final answer. It should be x plus 1 over x minus 1. All right, so our derivative of the inside, we're going to need the quotient rule. I'm going to need more space. I'm just going to write that there for now. That's the inside derivative. Make sure you don't write inside a second time. And then the outside derivative would be 3x squared with a red x. All right, so let's focus on the derivative of the inside. I'd call the top x plus 1 and the bottom x minus 1. Taking these derivatives, the top derivative would just be a 1 because the derivative of x is 1, the derivative of 1 is nothing. The derivative of the bottom function is also 1. It's actually quite simple. So the derivative of the x plus 1 over x minus 1. That's the derivative of the inside. Using the formula, it's the bottom times the derivative of the top. The derivative of the top must be in the first term. You could put the derivative of the top before the bottom or the bottom before the derivative of the top. But you can't have either the g or the f prime, top or bottom, respectively, be after the minus. These two things have to go before the minus. So going in the order, g means bottom. So the bottom is the x minus 1 times the derivative of the top, which is 1. So don't really need that parentheses because of that, because it's just x minus 1, but I want to be thorough. Then the minus from the formula, not a plus, a minus. And then it's top times derivative of the bottom. The top is the x plus 1 and we'll multiply that by the derivative of the bottom, which was 1. Remember, the quotient and the product rule, you end up using all 4 of these bits. Quotient rule, you also have that over the bottom squared, the bottom being x minus 1, so it's x minus 1 squared. We can clean this up, though. Distributing a 1 does nothing, so that's x minus 1 minus parentheses x plus 1 over x minus 1 squared. Distribute the negative, so that's x minus 1 minus x minus 1 all over parentheses x minus 1 squared. Combine like terms. X minus x cancels. Negative 1 minus 1 does not cancel. It makes negative 2. So negative 2 over x minus 1 squared. That is the derivative of the inside. Now we know the derivative of the inside and the outside, so we can do the chain. So f prime of x, or df dx, whichever way you like to write it. It's the derivative of the inside times the derivative of the outside. This is the derivative of the inside. This is the derivative of the outside, but remember, that's a special x that really represents the inside itself. So, derivative of the inside was the negative 2 times x minus 1 squared in the bottom. So that's the derivative of the inside, times the derivative of the outside, which is this thing, so that's times 3, and then the x, which really represents the fraction, x plus 1 over x minus 1, and then you're squaring it. Derivative of the inside, word for word, is right here. Again, this thing is the derivative of the inside. Start with a 3. This was the derivative of the outside, but making sure that you write the inner function where that x is, because that's what it really represents. All right, well, we got tops and bottoms that we can all put together. The negative 2 times the 3 is going to make a negative 6. Then you got an x plus 1 squared in the top. I'm just going to separate this as x plus 1 squared over x minus 1 squared. Then all over. There's your x minus 1 squared from the under the 2. And then here is the x minus 1 squared, and I'll show it in red. In the bottom, I just split up this thing being squared. The top squared over the bottom squared. The reason I did this is because now in the bottom, you got x minus 1 squared times x minus 1 squared. You can stack the exponents. 2 plus 2 is 4. So ultimately, this is negative 6 times x plus 1 squared all over x minus 1 to the 4th power. This is our f prime of x. What I think is interesting is this originally was all being cubed. The thing that was in the top dropped its exponent by 1. The thing that was in the bottom actually increased its exponent by 1. That goes in line with the power rule. But there are more complexities here because of the number. This 3 ends up bringing a 6 out front ultimately somehow. If these had been like a 2x plus 1 or a 7x minus 1, there would be extra multipliers in certain places because the derivatives of the top and the bottom would be numbers like a 5 or a 7 or whatever numbers I just said. But the basic core of the function, the basic idea is still kind of like, all right, if you just had the x plus 1, that would go from a cube to a squared. And if you had an x in the bottom being cubed, because of the way the algebra works, as we've seen, is the negative 3 turns into a negative 4, which is why the 4 goes in the bottom. So at least this part, the 2 parentheses, makes sense if you break it down that way. But the other numbers that come into play in and around this thing, you're never going to be able to predict just based on patterns. You have to do all this legwork. Okay, so let us show you that other notation that we mentioned, the other ways that the homework will do it occasionally. It mixes and matches. So the other notation is that you instead say that y is a function of u. You actually show the substitution like you would have done in pre-calc, taking like x to the fourth equation and boiling it down to an x squared, where you say let u equals this, u squared is this. It's kind of like that. So you have your original function y, and you're going to make it a function of u, where u is a function of x. So this is still showing a composition. Here's your f and your g, but now you actually show, instead of a red x, you use the letter u, so it's a different independent variable. It makes it a little more clear for some people, but not everyone. So when you do it this way, f prime of u, also known as dy dx, because your original function was in x, but now we're just showing it in u, is going to be dy du times du dx. This is still the chain rule. It's written in an opposite order though. The du dx, this part is the derivative of the inside times the dy du, that's your outer function. That's the derivative of the outside. So this is still the derivative of the inside times the derivative of the outside, but it introduces a fascinating algebraic concept into calculus that shouldn't work, but it does. All right, your original function was in terms of x. So you had y equals x squared plus x to the fifth minus parentheses, blah, 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 blah. So you were originally trying to find dy dx because you had y and your independent variable is x. But there were some complexities in the middle that required this little substitution, this which is the same thing as us calling an inside and an outside. Look at this. You got dy and you got dx. You still have this dy and this dx are here and here. But then for the dy part, you put it over du, and the part that is the dx, you put a du above it. I know every single one of you are looking at this and saying, oh, there's a du in a top and a du in a bottom. These cancel and just make dy dx. Calculus doesn't work that way. They don't actually cancel that way. It is a necessary evil to have it written that way. And that is exactly what the chain rule demonstrates. But what it does is it gives you a way to chain anything, whether it needs to be or not. If I had some function of z, and I wanted to take the derivative of x, maybe x was dependent on the variable u, and the variable u was dependent on the variable v. As long as I kind of have a du and a du in the top and a bottom of different ones and just make them cancel, if they were going to cancel, I get back to the original thing. So I could do dz du times du dv. Because u is dependent on v, I'd have to take that type of derivative for it. But v is dependent on x, so dv dx. It feels like algebraically the du's would cancel, the dv's would cancel, and you get the original derivative we were looking for. But again, this canceling doesn't really happen. It just feels like it would. Now, if this was a traditional calculus class, we'd be diving further into this idea. We're a business applied calculus class, so we don't. But I just at least want to take the very first example we did and show you how it could be done written with u's instead of the way I did it. And also, I like to actually write my chain rule a different way. I don't need to scroll up to see it. I've got it on my paper notes. I just got to find the page. Not that one. It was the 2x plus 7 cubed. So back to 2x plus 7 cubed. I'd say let u equal 2x plus 7. So f of u would now just be u cubed. That's the inside. That's the outside. Same concept, but now instead of using that fancy red X, it's a literal different letter, a U. So the derivative of this, if I say this is y equals, y prime is now the derivative of the outside times the derivative of the inside. Du dx is the same as u prime. Well, the derivative of the outside is 3 times u squared times the derivative of the inside is just a 2. Again, 3 in front. That's it. So the 3u squared, the derivative of the inside is just 2 because the derivative of 2x is 2, the derivative of 7 is 0. But we want our derivative to not have u in the answer. So we go back to our substitution. Well, u was 2x plus 7. So this is 3 times 2x plus 7 squared times the 2, which is really 6. And I could have multiplied the 3 and the 2 first to go ahead and get the 6. So 6 times the parentheses, 2x plus 7 squared. And that should be the same answer that we got originally, right? Yes, it is. It is correct. Honestly, this is a quicker way. This is the way I hope some of you pick up and do it ultimately, but I feel like as we start this idea, it's important to label things a little more methodically as insides and outsides. U is representing the inside, and then your function replaced with U is representing the outside. But again, in the final answer, you can't have U's, so it definitely just emphasizes the fact that you got to plug it in. You won't make that mistake with the red X still just being an X. All right, we got enough time to do one last example, and we'll call it a day. And let's go back to the tangent line stuff. For example 3, yay, we're going to find the equation of a tangent line to f of x equals 2 parentheses 5x minus 8 cubed at x equals 2. So we got a function, we got a x coordinate. We want to find the equation of the tangent line, which means we need the point and the slope. Well, the point would be very easy to figure out, f of 2. That's 2 times 5 times 2 minus 8 all cubed, which is 10 minus 8, which is 2, so that's 2 times 2 cubed, which is 2 to the 4th, and that's 16. So our point is 2 comma 16. That's half of what we need for the equation of the line, but it's the easy half. Now we need the slope. To find the slope, we got to do f prime. We got to do the derivative. Well, unfortunately, we're going to need to chain rule this. And I'm going to practice this doing the u stuff. Since I only did it once, let's do it one more time just to mix things up. If you need to write inside is 5x minus 8, outside would be 2 times a red x cubed, and then do those derivatives independently, that's fine as well. I'm just going to show you the other way. So we let u be the inside, which is the 5x minus 8. So that's what we call the inside. Then the outside part is now f of u being 2 times u cubed. That's what we call the outside. And then our derivative, f prime of x, would be the derivative in terms of u times the derivative of u. So f prime of x, the derivative of the function in terms of u, that's the derivative of the outside, would be 2 times 3 times u squared. Bring the 3 out front, drop the exponent by 1. So that's the derivative of the outside times the derivative of the inside. The derivative of the inside would be 5. If you need to see that, inside derivative is 5. Outside derivative would be 3 times 2u squared. So times the derivative of the inside, that's the 5. Well, 2 times 3 times 5, you can clean up all of that, right? 2 times 3 is 6, 6 times 5 is 30. So this is 30 times u squared. But this is supposed to be a function of x, not u, so we go back to x. So f prime of x is 30 times 5x minus 8. That would have been the red x we had before, squared. This is our slope formula. So our slope m should be f prime of 2. Remember, we're doing this all at the x value of 2. That's 30 times 5 times 2 minus 8 squared, which is 30 times 5 times 2 is 10. 10 minus 8 is still 2. That's 30 times 2 squared, which is 30 times 4, which is 120. So that's our slope. So remember, equation of line, y minus y1 equals m times x minus x1. If you don't remember that, shame. You need it. So the x1 and the y1 were the 2 and the 16. That's the x1 and the y1. So we go y minus 16 equals, the m was the 120 times x minus the x1, which was the 2. That's y minus 16 equals 120x minus 240. We're then going to add 16 to both sides, giving us our equation. Y equals 120x minus, that's 224. So the slope is 120. The y-intercept would be 0, negative 224. And if you sketch the curve and the tangent line, you could see that it would be touching and going at the coordinate x equals 2. So we're going to call it a day there. We've done enough with this chain rule in our almost 2 hours. I don't really want to introduce the last section, which is on higher order derivatives, but I'll
Sorry about that. Didn't mean to hit play again. All right, just give me a second. All right, so here's where we're going to start 1.8, the last section of chapter 1, higher order derivatives. And yeah, like I said, we'll definitely finish that tonight. We're going to take our break in about 55 minutes and continue from there.
is.
I just realized I had my screen paused and y'all weren't seeing any of that. Okay, sorry. So I'm assuming that you did not hear me say we're going to start 1.8 higher order derivatives and you missed that whole minute. So starting back from here, here we go.
Higher order derivatives. The last section that will be tested on for test 1. Higher order derivatives. So up to this point, we have been finding first derivatives only. So every time we've done a y prime or dy dx or f prime of x or df dx, those were all first derivatives. Second derivative found by taking the derivative of a derivative of the first derivative. A second derivative is the derivative of the first derivative. A third derivative is the derivative of the second derivative, et cetera, et cetera, et cetera. Now, some of these problems are quite easy and short. Some of them are longer. It depends on the complicated nature of the function. If your function is a polynomial and you're just applying a power rule to get the first derivative, the second derivative is probably going to be the same difficulty. And sometimes they actually get easier and easier and easier as you go. But if taking the first derivative involves a product rule or a quotient rule or even a chain rule, it's very likely that that's going to continue moving down to the second and third and fourth derivatives. So they're usually about in the same complexity to find the second derivative as first derivative, which means if it takes you 4 minutes to find the first derivative, it might take you 4 or 5 minutes to find the second. If it takes you 10 or 15 seconds to find the first, probably going to take you about 10 or 15 seconds to find the second. All right, so given, let's just put this in notation instead of just language. Given some function f of x, and I'll show the notations with regular old y's after the fact. So given a function, its first derivative is f prime of x. No surprise there, nothing new there. The second derivative, where did my pen go? Cut off for a second there, that was really weird. The second derivative we label as f double prime of x. So there's two of those little quote marks. It looks like an actual quotation now, or two little Roman numeral ones without the horizontal parts. So this is us taking the derivative, taking d dx of the first derivative. Again, this is all just notation. This is saying that to find the second derivative, you take the derivative of the first derivative. The third derivative, and yes, I'm abbreviating derivative, that's f triple prime of x, which would be d dx of f double prime of x. The fourth derivative would be f. Now, I see people do this differently. I've seen people actually write IV for 4 to kind of go with what feels like these were Roman numerals, I suppose. And this would be the derivative, d dx, of f triple prime. But I also see, this is the same thing, the fourth derivative, f, and then just the 4 marks. I've seen it both ways in different texts and different teachers and different people. And it's still the same ddx of f triple prime. So I don't care which notation you're using in your own paper pencil stuff. My math lab will make the choice. And I think I saw it using the 4 lines. But again, it doesn't really matter. I also see some people do this, where they put an actual 4 in parentheses above the function. So this is denoting a fourth derivative as well. So there's 3 different ways you can write that, and that's just inside one of the notations. We haven't even gotten to the, what does this look like as a dx with 2s and 3s and 4s. So the other notation, you have your regular old function. You have your first derivative, which would be df dx, no surprise there. You have your second derivative, which looks like this, d2f dx squared. Then your third derivative looks like d3f dx cubed, et cetera, et cetera, et cetera. I'm not going to write et cetera. I'll write the fourth one since I did 4 on the others. And then your fourth derivative would be d4 f dx to the 4. So what's interesting in this notation, in the Leibniz notation, is that the 3 goes on the x on the bottom, but on the d in the top. It's not the d in the top and the bottom. It's the d on the top and the variable on the bottom. And again, that's because these aren't being cubed. It's just showing that we took a d dx to 1 or 2 or 3 times. If you go back to this other notation, taking d dx of f prime, if you switch these to the d dx notations, this is kind of the reasoning why. Let's say the third one would be d dx of d dx of d dx of f of x. It kind of feels like you're multiplying the d dx, d dx, d dx. If you were, that's d cubed dx of the f of x. But we just typically write it with the f in the top instead. That's the reasoning behind why we cube the d in the top and the x in the bottom. And again, these aren't cubing, that's just a 3. I shouldn't even say it looks like it's cubed. Those 3s are notating how deep we are in the rabbit hole of the derivative. And there are physical relationships between a regular function, a first derivative, quite often its second derivative, sometimes even its third derivative, and depending on what we're talking about, we can even get into a fourth and fifth derivative and have some kind of discussion as to what it means. Admittedly, we usually don't go that far down the rabbit hole. We stick to first and second derivatives in this course primarily. The only real time I can tell you that a third derivative is interesting at our level deals with objects in motion. And I'm going to take a pause on that since I don't want to spoil too much all at once. Again, all we've done so far is just labeled notation. I haven't given you any formulas. There are no formulas. There are no new formulas in this section. This entire section is just take a derivative and then take another derivative and maybe take another derivative and maybe take another derivative. Take as many as they tell you to. And when we get into later sections where we're going to do very deep graphical analysis stuff we couldn't have even done in pre-calc, that's where that first and second derivative really come into play. We don't really need anything past the second for graph analysis, but we will need the first and second. Okay, so let's actually get down to brass tacks. Let's try this out. I know you're sick of me rambling. So example 1a. For example 1, let's find, I want to make sure I label this appropriately. Yes, find the first through fifth derivatives. Are we doing it for all of those? Yes. For A, find the first through fifth derivatives. For the function x to the fourth minus 3x squared plus 9x plus 7. So there's our original function, whether we call it an f of x or a y, it doesn't matter. And by the way, if we were using y's, you have y. Why did my pen turn off? I'm hitting a weird button today. You have y, that's your regular function, then you have your y prime, then you have y double prime, y triple prime, y to the fourth, it looks like, but that's really the fourth derivative. So that's your function, first derivative, second derivative, third derivative, and fourth derivative. All right, so with f of x being x to the fourth minus 3x squared plus 9x plus 7. I'll go in red. F prime of x, the first derivative. Now this is just a straight up polynomial with no products or quotients. This should be easy. It is my opinion that no calculus student should ever miss a power rule on a test. It is inexcusable because it is the simplest rule and we use it hundreds, if not thousands of times throughout the semester. The power rule being bring the exponent down and decrease the exponent by 1. So for the x to the fourth, we bring the 4 down. Then the exponent goes from 4 to 3. For the next bit, there's a minus, so don't forget that. Then 3x squared, we're going to bring the 2 out and multiply it by the 3. The 2 times the 3 is a 6. Then we decrease the exponent by 1. I'll write the 1 for just a hot second, but I'm going to make it disappear because I don't want to get confused. So 6x to the first, the 2 dropped to a 1. But again, I don't like writing that 1, so I'm not going to write it. Then plus, for the 9x and the 7, these are the special cases. The derivative of a linear term is just a coefficient, so that's just 9. And the derivative of a constant is 0, but we generally don't write zeros. So we just leave the 9 there. So there's our first derivative, 4x cubed minus 6x plus 9. That's one of the answers. That's the derivative we've been finding normally so far. But now we're going to study the second derivative, especially heavy coming up. So the first derivative is the change of a function. The second derivative is how the change is changing. And it takes a little bit for you to wrap your brains around what that means. How is the change changing? Is the increase increasing? Is the decrease increasing? What the heck does that mean? How do we use it? We'll get into that later. For now, we're just working on the mechanics. So now let's go to the second derivative. F double prime, or d2f over dx squared. So I'm going to write this for a second and then I'm going to erase it. I could also write d2f over dx squared. That would be the same thing. Okay. So we're taking the derivative of this thing now. We are focusing all our attention on the first derivative to get to the second derivative. So we don't even want to look at this anymore. I'm going to erase my scribbles, but we're ignoring that one now. So we're looking here, 4x cubed minus 6x plus 9. So for the 4x cubed, we bring the 3 down. 3 times 4 is 12. Remember, coefficients get multiplied by the number brought down. Now we have our x, and we decrease its exponent by 1. So it goes from 3 to 2. Okay. Sorry, my dog was making a funny noise. All right, distraction's over. Minus. Now this 6x, this is a linear term. There's no exponent on the x, so its derivative is just the coefficient, which was the 6, the minus 6 specifically. And then for the plus 9, that's a constant. The derivative of a constant is 0, which we don't write. Don't have to write. So this is our second derivative. And that's it. Third derivative, f triple prime of x, or d3f dx3, depending on how you like writing it. So now we're focusing our attention on just the 12x squared minus 6. The derivative of 12x squared, you're going to bring the 2 out front and multiply it by the 12. 2 times 12 is 24. Then the exponent gets decreased by 1, so the 2 turns into a 1, which once again I will not write permanently, just showing you. Then for the minus 6, the derivative of constant, it's the fourth time we've said it today already, is 0. So that's the third derivative. We're supposed to find the first through the fifth. Now moving forward in this course, we are very, very rarely, if ever, going to go past the second derivative in general for more advanced studying. But it's not to say that we can't just find them if asked. Now my preferred notation is this, and some people will even put the IV in a parentheses, but that's just the Roman numeral 4. Some people like to go like this. Some people like to just put a little 4 in a parentheses. It's up to your textbook, it's up to your teacher. I accept them all. I can't remember which one my math lab does off the top of my head. I was actually more looking into the homework for chapter 2 before class started versus this one, so I wasn't thinking about that. But again, I'm showing you them all. Use whichever one they're using, and you won't even have to type it in there. They should have it typed for you. And on a test, I'd accept all of them. So again, me personally, I like the Roman numeral just to change gears a little. So the fourth derivative of x. So again, we're focusing our attentions on the third derivative. 24x is just a linear term. The derivative of a linear term is the coefficient. So 24x has a derivative of 24. And that's it. There's nothing else. Finally, the fifth derivative, which would be fv, or f quintuple prime if you want to read it that way. That's the derivative of this 24. The derivative of a constant is 0. Again, special case. So the fifth derivative is 0. That's all 5 derivatives. First, second, third, fourth, fifth. Nothing too crazy. I want to point out something though. And I'll do this in a different color. If you went and tried to find the sixth derivative, fv1, and this is why I don't like using this. This looks just silly, doesn't it? No one ever does that. So if you try to do the sixth derivative, well, the derivative of 0 is 0. If you try to do the seventh derivative, the derivative of 0 is 0. If you try and do the eighth derivative, the derivative of 0 is 0, and so on and so forth. So if at some point when you're taking these derivatives of derivatives, if one of them becomes 0, the rest of them are 0. This doesn't always happen. It happens with polynomials, but it doesn't happen with weirder functions. So what I like to do on a traditional math test is I'll give a problem where I say find all the derivatives, and the student has to figure out where to stop. And I will even admit that most students, if I say find all derivatives, they end up stopping here, but that would be incorrect. They're really supposed to stop here. You're supposed to show getting 0 if I ask for all derivatives. So if I were to do that on test 1, I'm not saying I am, I said if I ask for all derivatives, make sure you get to the one that's 0. If you don't, you are making a mistake. All right, let's do another. F of x equals, and let's step up the difficulty, 3 over x, and we're going to find the first 5 derivatives once again. So this problem is not as easily completed because it's in a bad setup. It's in a bad setup because we need the power rule. Now you could arguably use the quotient rule, but you're making this problem way too complicated if you do it that way. the power rule would be much better to apply for this one. But we can't use the power rule right now because the x is in the bottom. So we have to change this to be 3 times x to the negative 1. It's not something we haven't seen before. Double negative means we've seen this before. Now we can apply our process of the power rule. So our first derivative, we bring the negative 1 down, times the 3. I'll show the work this time. And then the x, decreasing the exponent by 1, negative 1 minus 1 is negative 2. Remember, when you have negative exponents starting out, when you apply your power rule, they go further and further into the negatives because when you subtract 1, it makes the number smaller. Negative 1 minus 1 is negative 2. Negative 2 minus 1 is negative 3. Negative 3 minus 1 is negative 4. You're going to keep seeing these grow in terms of negatives. So this is really negative 3 times x to the negative 2. Now I'll rewrite this in the end, but let me leave it this way for now. Again, I will write this as negative 3 over x squared ultimately, but because I need it this way for the next derivative and the next derivative, it's going to benefit me to leave it this way for a while. So when I go to do the second derivative, I'm going to bring the negative 2 down times the negative 3. And then the exponent gets decreased by 1 from negative 2 to negative 3. That product in the front is positive 6, so that's 6x to the negative 3rd. The third derivative, we're taking the derivative of what we just got. So we bring the negative 3 out front, times the 6 that's there, and we decrease the exponent by 1. Negative 3 times 6 being negative 18. That's negative 18 times x to the negative 4th. Then the fourth derivative, I'll write it this way this time with the 4 in parentheses instead of the Roman numeral, just so we see it all the different ways. So we're focusing on the negative 18x to the negative 4th. We bring the negative 4 down, times the negative 18, and then the exponent gets decreased by 1, so it's a negative 5. Well, 2 times 18 is 36, times another 2 is 72. The negatives cancel. So that's 72x to the negative 5th. And yes, that's how I multiply in my head. Now the fifth derivative. Taking the derivative of the 72x to the negative 5. So we bring the negative 5 out front, times the 72. Then decrease the exponent by 1. Negative 5 minus 1 is negative 6. Please show that arithmetic if you have to. That is up to you if you need to be showing your arithmetic. I can't tell you what arithmetic you need to show and what you don't. It depends on your skill level. I think that's obvious. But you should be able to do that without a calculator. If you need a calculator to do negative 5 minus 1, I'm terrified for what happens the rest of this semester. All right, 10 times 72 is 720. Half of that is 360, so this is negative 360. And yes, that's how I multiply even numbers in fives. That's x to the negative 6. But now let me go and rewrite my derivatives in the more appropriate form. Since the original function was written this way without negative exponents, it's probably in our benefit to write the actual answers the same way without negative exponents. It was good to leave them that way to go deeper into the rabbit hole to get the derivative of a derivative of a derivative, but now we want to clean them up to the better format. So f prime of x, that was this one, the negative 3x to the negative 2, that would be negative 3 over x squared. F double prime of x, the second derivative, that was the 6x to the negative 3rd, that becomes 6 over x to the positive 3. I'm not changing the sign of the polynomial. The negative 3 stays negative 3. The positive 6 stays positive 6. The 3 and the 6 don't go to the bottom. It's just the thing with an exponent that's negative, just that. F triple prime, the third derivative, that was over here with the negative 18. So negative 18 over x to the 4th. The fourth derivative was the one with the 72. So that's 72 over x to the 5th. And then our last that we found, the fifth derivative, was the negative 360 over the x to the sixth. There's an obvious pattern here in the bottom. The exponents in the bottom are bumping up 1, and that's because when you put them in the appropriate form with the negative, when you decrease them by 1, it makes the negative get bigger, so to say. And again, these notations could have been df dx equals negative 3 over x squared. This could have been d2f over dx squared equals 6 over x cubed. This could have been d3f over dx3 equals negative 18 over x to the fourth. I won't write all those. You get the point. It's just different notation. People have different ways they like to read and write things. So we have y equals and we have f of x equals. So we have Leibniz notation versus Newtonian notation. Okay. Let's do another. And for C, that was A and B had the same instructions for find the first 5 derivatives. I just didn't write the instructions for B. For C, we're only going to find the first 3 derivatives, and I'm going to bump it down to here. So we're not going to find the 4th one or the 5th one. These are going to be more time consuming, and that's why. So for our f of x or our y equals, whatever you want to call it, this would be 8 square root of x, which is in a terrible format. It is in a terrible format because we could apply the power rule if we change the format, but we can't do it right now. This square root of x is much better written off for calculus as 8 times x to the 1/2. It's a lot more understandable in an algebraic sense as 8 square root of x, but to apply a calculus formula, you have to understand changing these two things. That's why we really hammer this stuff out in pre-calculus. Now we can do our derivatives. So f prime of x. Bring the power down. So that's 1/2 times the 8 that was already there. And then we'll decrease the exponent by 1. I'll show the fraction math up at the top. You've seen this before, but 1/2 minus 1 is 1/2 minus 2 over 2. Once again, no excuse for not being able to handle addition and subtraction or multiplication and division of fractions. You're going to do it all the time in here. 1 minus 2 is negative 1, so that's a negative 1/2. Now again, I'm going to wait till the last minute to... What just happened? Why did that erase? I didn't hit anything. That's the weirdest thing I've seen so far today. Technology. I miss whiteboards. I really do. It was like me just doing that made it erase, and I didn't click my button. Whatever. I'm distracted. Sorry. So again, I'm not going to change the format yet. I'll wait till we get all of them. Oh, and I don't want to do that yet. I want to, the 1/2 times the 8 is obviously a 4. So this is 4 times x to the negative 1/2. Now let's go to f double prime of x, or y double prime, or d2f dx squared, however you want to write it. Bring the exponent out front, negative 1/2 times, leave the 4 there. The x to the negative 1/2, we got to drop the exponent by 1. So negative 1/2 minus 1 is negative 1/2 minus 2 over 2, which is negative 3/2. I was trying to erase it again just to see if me writing it really quickly then doing that. Nope. The negative 1/2 times the 4 obviously being a negative 2. So negative 2 times x to the negative 3/2. The third derivative, bring the negative 3/2 out in front. Leave the negative 2 there. Then its exponent needs to drop by 1. Going back up here. Negative 3/2 minus 1 is negative 3/2 minus 2 over 2, which is negative 5/2. So you could probably guess that the next one would be negative 7/2, the negative 9/2, the negative 11/2 if you're good with patterns. The 2's will cancel, the negatives will cancel, so this is just negative 3 times x to the negative 5/2. I only said to go to the first through the third derivatives That's the third derivative, so we can stop. So our answers, f prime of x, that was this one, the 4x to the negative 1/2, but we need to bring the x to the negative 1/2 to the bottom. So that's 4 over x to the positive 1/2. But that's 4 over the square root of x. So that's our first derivative. X to the 1/2 is square root of x. You've got to know how to convert from your rational exponents to your powers. I'll write that one last time in a different color. The nth root of x to the m is x to the m over n. If you don't know that, you're going to have a hard time making anything better than a C in this course. Someone asked a question. Why is 3 negative if the 2 already was? Why is 3 negative if the 2 already was? Oh, you know what? That was a typo on my behalf. I had this negative in my head when I wrote that. I said it at first that these two negatives canceled, but then I didn't cancel it. I just wrote it on accident. That's my bad. Good catch. Please make sure that you catch that I'm erasing. I'm erasing that negative there. These two negatives do cancel, as I said, but did not write. Once again, thank you for catching that. And this is why I would hate doing a recorded lecture, because no one would have caught that until hours later. Okay, back to where we were, the f double prime of x. So that was the negative 2x to the negative 3/2. So that's negative 2 over x to the positive 3/2, which we can write as negative 2 over. With the 3/2, the 2 means it's a square root of an x cubed. So that's our f double prime of x. Then our third derivative, f triple prime of x. That was the positive 3x to the negative 5/2. So that would be 3 over x to the positive 5/2, which would be 3 over the square root of x to the 5th. That's our third derivative. First, second, and third derivatives all in play. So here's something else to take away. Not only did we see the x's go negative 1/2, negative 3/2, negative 5/2, negative 7/2, negative 9/2, negative 11/2. What you'll also notice is that the coefficient of all these derivatives keeps oscillating from positive to negative. And that's something that I would have caught in the next second, because I was about to make that point and I would have been, oh, no, I made a mistake here. So this was a positive, then a negative. This one's a positive. The next one would be a negative. And that's because you keep bringing a negative out front and multiplying by one more negative each time. That's what causes this sign oscillation of a problem like this one. Does that always happen? No, it happens in problems like this one. It also happened in the last one, didn't it? Yes, it did. Negative, positive, negative, positive, negative. And that's because we had variables in the bottom. Variables in the bottom cause us to bring negatives to the front. So you just get used to seeing these patterns. You start recognizing them, and then it can make you be able to check things really quickly. And like I said, I would have just now caught the mistake here when I tried to make that point and go, oh, wait, no, I said something earlier and then wrote a negative on x. All right, let's do one more of these. So D. And let's only do the first two derivatives on this one, because it's going to be much more complicated. And this function is going to be x squared plus 1 over x. Uh-oh, we got a quotient rule. So quotients and products and chains can all end up being used to find the derivative of a derivative of a derivative, as I was alluding to earlier in the day. Hold on. Had to cough and get some water there. Okay. So this is a quotient. So we need to use the quotient rule. Arguably, asterisk, arguably, you don't need the quotient rule for this particular problem because the bottom is a special case. And in the word problem we did last class, we did the same type of problem. We took a derivative of something like this because the bottom only had one term. You can actually split this fraction and do this a much easier way. However, I want to practice with the quotient rule since we didn't last time on that example. So we are going to use the quotient rule. But I'll at least make the little memo here. Because the bottom is one term, you could split the fraction to avoid the that's going to be annoying. Quotient rule. But I'm going to do it the more difficult way. Once again, the reason is because last class I did an example using that memo, avoiding the quotient rule, but I think we should practice with the quotient rule one more time. And I will even remind us what that quotient rule is. The derivative of a top over a bottom, I'll write it out that way this time, is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Again, the order of each thing in the term, the b and the t prime can swap, the t and the b prime can swap, but that's it. You can't swap the order of the terms because of the minus. Oh, and let me actually write out what the top and the bottom are. So for f prime of x, for finding the first derivative, that looks funny. The top is x squared plus 1, and the bottom is x. The derivative of the top would be 2x. Bring the 2 down, decrease its exponent. For the derivative of the 1, it's nothing. For the derivative of the bottom, the derivative of x is 1 because there's a 1 in front. That's the slope. Special case of the power rule. So those are the 4 things we need to put into that formula there. So f prime of x is going to be the bottom, which is the x, times the derivative of the top, which is the 2x, we're multiplying these two, minus, now we'll multiply these two. The top, which is the x squared plus 1, going to need that in parentheses because of the minus, and maybe even because of the product, times the derivative of the bottom is 1. All over. Now once again, this was the bottom times the derivative of the top, minus the top times the derivative of the bottom. All over the bottom squared. The bottom was originally the x, so now that's an x squared. Again, this right here is the original bottom, and we square it. That's just part of the formula. We can definitely clean this up. X times 2x is 2x squared. Multiplying a parentheses by 1 does nothing, so this 1 at the end does nothing. We're just distributing the negative. So then a minus x squared and a minus 1. Again, that was giving the negative to the x squared and the positive 1. And that's all over x squared, which tells us f prime of x, the 2x squared minus the 1x squared gives us a 1x squared, but I don't need to write the 1. 2 minus 1 is 1. Then the minus 1 at the end, then over the x squared. That is our first derivative. Now this derivative is a quotient. Typically, if you start with a quotient, its derivative is a quotient. If you start with a product, you can typically write the derivative as a product. Again, notice I'm using the words typically. I've got quantifiers. I'm not making absolute statements in here. All right, I'm going to change color for the second derivative in the interest of sanity. So for finding f double prime of x, the last one we have to find, its top and bottom, we're using this right here. The top is x squared minus 1, which the original top was x squared plus 1. It's similar, but different. They don't have to be that similar. They can be more different than that. The bottom is x squared. Take these derivatives. So the derivative of the top, the derivative of 2x, I'm sorry, the derivative of x squared is 2x. The derivative of negative 1 is 0. Then the derivative of the bottom would also be 2x. It's kind of a interesting coincidence that they're both 2x. That happens sometimes. And now we can apply the formula, which is bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Or the top, or the derivative of the top times the bottom minus the top times the derivative of the bottom. There's a lot of different ways to write that, but not nearly as many as a product rule. Okay, so f double prime of x, using the formula, the bottom times the derivative of the top, so this product, I'm sorry, excuse me, the bottom times the derivative of the top is these two. The bottom times the derivative of the top. Oh, I hit save on accident. Oh no, this is gonna crash. Oh, it didn't. Sweet. Usually when I hit save on these, it crashes. It's a really big problem. I got lucky there. So again, the bottom times the derivative of the top is these two. So the bottom is the x squared times the derivative of the top is the 2x. Minus then these two. So the top times the derivative of the bottom. So that's x squared minus 1 times the 2x. Don't forget the all over, and that's the bottom squared, which is x squared squared. And we can definitely clean this up. The x squared times the 2x in the front is 2x cubed. Just count this as a minus 2x. This right here is a minus 2x. So again, I'm just giving the negative to the 2x. In fact, I'm going to just swap the order of the product. So minus 2x parentheses x squared minus 1 all over x squared squared is x to the 4th. You multiply those exponents. It's just a coincidence that 2 plus 2 is 4. You multiply them. So this is 2x cubed minus, so this negative 2x times x squared is going to be a negative 2x to the 3rd. Then the negative 2x times the negative 1 would be a positive 2x all over the x to the 4th, giving us, finally, that the second derivative, the 2x cubed minus the 2x cubed is going to cancel. These terms cancel each other out. So we're just left with the positive 2x over x to the 4th. It actually looks simpler than the first derivative. The first derivative had 2 terms in the top. This has only got 1. That's because this canceled better. But here's the thing. If you stop here in my math lab, it's not going to mark it right because this is reducible. Because this is a simple monomial over a monomial, you must reduce this. So the second derivative, you'll lose an x in the top and bottom, and you'll get 2 over x to the 3rd. So again, that problem is definitely a little more complicated because of the quotient rule. I'm not going to do any with the product rule because, well, it's easier than the one I've just done. And the chain rule is just literally chaining a chain. So I want to leave some types of examples open to y'all to have to try on your own. I am not here to give you every single exact type of example that you would see in homework. That's not what we do in a calculus class. We teach you enough to be able to extend that knowledge and learn, because that's how you grow, not just copy pasting. But however, in the homework, as you've seen, those of you working on the homework, which not everyone is, but those of you working on the homework know that most problems offer the view an example and help me solve this. So just because I don't show you something, generally speaking, you can use that as a backup plan. All right. So let's get to the main application of this section, which is objects, motion. And some of you might be familiar with a particular property that an object in motion tends to stay in motion unless acted upon. It's a fundamental property, but not something we're using in here. We're more talking about just position, velocity, and acceleration. Position says where an object is. Velocity says an object's speed and direction. Acceleration is the change in speed of the object. Note, speed or velocity, no matter which one you're talking about, is a change in position. Notice these key words we're using. Change, change. Change is derivatives. Remember, calculus says change means derivative. Let's just bump this all down. And to the person that sent me a private note, that's fine. I'm glad you're back. So the things that we'll study with objects in motion are their position, velocity, and acceleration. So when you're on the highway, you can describe your location based on a position function, arguably, if you are traveling in a predictable manner. You can describe your velocity, which is your speed and direction. Speed doesn't have direction, just magnitude, just size. That's what magnitude means. But velocity gives you direction, whether you're moving left or right, whether you're moving northeast or south, southwest, whatever it might be. So velocity is the change in position, which means that velocity is the derivative of position. If acceleration is the change of velocity, then acceleration is the derivative of velocity. But check this out. Velocity itself is a derivative. Specifically of position. So since velocity is the derivative of position, that means we can say the acceleration is the derivative of the derivative of position. In other words, acceleration is the second derivative of position. They're all three related. If you have position, you can get velocity by taking a derivative. You can get acceleration by taking its second derivative. It's just working down the chain. We tend to denote these with specific letters. Position as a function, we usually use an S of t, t for time. Velocity, we usually denote with the letter V. And you might say, well, why not use the letter P for position? I've made that same argument. Not everything in math is logical in terms of naming things. So velocity is V of t, not V of s, excuse me. And it is equal to s prime of t. It's the first derivative of position. And then acceleration, acceleration, we denote with the letter A of t. And it is the first derivative of velocity, or you can say it's the second derivative of position. I'm just going to use the actual quote. There we go. Position is your primary function. That's the main function. To get its velocity, aka speed with direction, you take the derivative of position. To get acceleration, you take the derivative of the thing you just took a derivative of. So that's why it's in this section. So the reason our independent variable here is t is time. It could be in seconds, it could be in minutes, it could be in years, it could be in months, it could be in days, it can be in anything. It's generally denoted. The position or the velocity, they're all measured in meters or meters per second. Acceleration would be meters per second squared. And again, that's just based on meters. It could be miles, it could be inches, it can be anything. So let's just say meters, etc. The velocity would be meters per second, etc. Could be feet per second. It could be meters per day. It could be miles per hour. And then acceleration, the weird one, it would be meters per second squared. The squared part has everything to do with this part. And again, the algebra and calculus notations and their meanings do not fully line up. This is not a d times an x cubed. That's not what's happening here. But the fact that we're cubing a unit in the bottom, that's what it looks like is we're cubing a unit in the bottom. That's what leads to us kind of having this argument that we're now would be cubing the units in the bottom or squaring the units in the bottom. Every time you go one layer deeper in a change, that's a per something. So if you're originally per second, when you go to acceleration, you're doing per second, which if you combine the per second, it becomes per second squared. If you went to the next derivative, it would be per second, which would be per second cubed. Don't try and think about what that really means. I have definitely caused some scars on my brains thinking about it, or wrinkles, whatever they are. And I think a lot of people do too if they try and overthink what it means to be a per second. Just take it as a label, but you need to have your labels appropriate. So for our example, what are we up to? 2, I believe. Yes, for our example 2, which
which we will get to when we come back from our break. So let's come back at 8:03. So we're going to come back at 8:03. All right, picking up with example 2.
From our text is example 3 in the text. They say, from the point at which an object is dropped from a cliff, find each of the following. I'm sorry, I'm jumping sentences. The distance falls in t seconds, so time is measured in seconds for this problem, is about S of t equals 4.9 t squared. This is a very common term for falling objects. Now, we are making some assumptions here. We're assuming there's no air resistance. So we're assuming that we're dropping this item in a vacuum. Now, ultimately, that's a poor assumption if you're going to let this thing drop hundreds and thousands of feet. But if you're only going to let it drop a few seconds and it's not a piece of paper or something that just really kind of defies the normal falling mechanics, so think about dropping a ball, something like that, with an even weight distribution, then this is a pretty good approximation for a couple hundred feet, in fact. But after that, air resistance starts kicking in, and eventually objects slow down, because this says that the position is going to keep increasing and increasing and increasing in a squared manner, which means that it's constantly accelerating, as we'll see. And that's not true in real life. There is kind of a peak. But again, so we got this position function. We're going to, and where S is measured in meters, find how far a stone would drop after 5 seconds. I need to give myself a little more space. Then find its speed after 5 seconds. Then find its acceleration after 5 seconds. You can call that a part A, B, and C if you want. And instead of speed, I'll use the better word velocity. I think the text used speed. No, they use velocity. That's good. That's better. So we want the position, the velocity, and the acceleration of this stone after 5 seconds. Well, the velocity, we said we denote with v of t. That's the derivative of the position function. So we need to take the derivative of 4.9 t squared. So we bring the 2 out front. We multiply that by the 4.9. And then the exponent gets dropped by 1, so that's a 1. But again, I don't leave 1 exponents written anymore. So that's 2 times 4.9t, which 2 times 4.9 is 9.8 t. So this is our velocity function, 9.8 times t. Let me make my t a little better. I like to make my t's a little curly in the function so they don't look like plus signs. So that's our velocity. I'm just going to go ahead and find the 5 functions and then actually go through and plug in the 5s. Our acceleration, which we denote with a of t, that's the second derivative of the position or the first derivative of the velocity. You can write it either way. It's s double prime of t, or you can write that as v prime of t. You're just taking the derivative of what we just got. So we take the derivative of 9.8t. Well, that's a linear term, which means we just get rid of the variable. It's 9.8. That's the acceleration. So we have our position function. If we plug in any time in seconds, we can tell where this rock is in terms of the height from its initial starting point. So we're calling the initial height 0 with this model. We can say its velocity and we can say its acceleration. And we were specifically interested at what happens 5 seconds in, its position, speed or velocity and acceleration. So now we'll just plug in 5. So we're going to plug in 5 into this, and this. So we'll do S of 5. Which is 4.9 times 5 squared, which is 4.9 times 25. I'm not going to do that in my head. It's 122.5. Now, we said that this position was measured in meters, so that should be 122.5 meters. So that's how far it's fallen. It fell. So in 5 seconds, this thing has fell 122.5 meters. If we find the velocity, so we're plugging the 5 in to the velocity now, which was just 9.8 times t. So 9.8 times 5. And if you double, if you take 98 times 10, 9.8 times 10, you get 98. If you half that, you'll get 49. So this would be 49. Now it's not 49 meters, it's 49 meters per second. So this is the speed 5 seconds in. That other part was how far it's fallen 5 seconds into dropping it. Finally, the acceleration. Well, the acceleration function is just 9.8. There's nowhere to plug it in. This says that the acceleration is always 9.8. So it's 9.8 meters per second squared. That's the acceleration. 5 seconds in. I know I got sloppy there. So what does this information tell us? Well, it says that over the next second, our speed is going to increase another 9.8 meters per second. So again, what this says is the acceleration says that the velocity will increase approximately, or maybe exactly, it just depends. In this case, it's exactly, but it can just be approximately, by 9.8 meters per second. The velocity says that the position will increase, again, approximately, not necessarily exactly, 49 meters. And these are supposed to be from seconds 5 to 6. So that's the bigger statement that you can take away from that. So our we're picking up speed because the acceleration is positive. Our position is increasing because our velocity is positive. And because there's acceleration, that means our speed is increasing and increasing and increasing, which means our position is going to increase and increase and increase over time. If you don't believe me, the textbook does not do this, but I want to plug in 10 seconds now. So let's ask us, as an extra problem, what happens 1 and 10 seconds in? Sorry, I didn't say the 1, but I meant to. So we're going to plug 1 into these three things, and then we're going to plug 10 into these three things and see what we get. So, and I'll skip the color, but S of 1, that's 4.9 times 1 squared. 1 squared is 1, so this is just 4.9 meters. So after 1 second, we have only fallen about 5 meters. I don't know why I said 4.5. But in the next 4 seconds, we fall 122. That's because our object has not been picking up speed. It hasn't been accelerating very long. V of 1, that's the 9.8 times the time. So 9.8 times 1 is 9.8. So our speed at this point is just 9.8 meters per second. And then our acceleration at 1 is just 9.8 meters per second squared. Notice that the acceleration is the exact same, but the position and the velocity are a lot smaller. It's the fact that the acceleration is a positive number, which makes the velocity pick up steam, which makes the position pick up steam and pick up steam and pick up steam. So it's got a kind of a slow start. But then after 5 seconds, now instead of falling half a meter, in those next 4 seconds, we fell another 117 meters. In fact, let's do S of 3 as well. I'll get to 10. So that's 4.9 times 3 squared, which is 4.9 times 9, which is close to 49. It's 44.1 meters. So in the first second, we fell 5 meters, add 2 more seconds on, and we managed to fall 44.1 meters. So we picked up another 40 meters practically in 2 seconds. So the position is going to keep increasing in a quadratic form. The velocity, 3 seconds in, would be 9.8 times 3, which is 29.4 meters per second. And the acceleration 3 seconds in is just 9.8. So we can really see that we're picking up speed. We went from 10 meters a second to 30 meters a second pretty much. Our acceleration did not change. The acceleration is what's causing the increase in speed. And because our speed is increasing, oh, there's that magical erase thing that just happened. Because our speed is increasing, our position is increasing quicker and quicker and quicker. Now then you got your 5s. So in the next 2 seconds, we went from 44 meters to 122 meters. Our speed has gone from 29 meters per second to 49 meters per second. So we're almost at highway speed. Now let's check out 10 seconds in. So 4.9 times 10 squared is 4.9 times 100, which is 490 meters. So now in 10 seconds, we've fallen 490 meters. 5 seconds in, it was only 122. So we went from 100 to 500 pretty much in 5 seconds. The velocity is just 9.8 times 10, which is 98 meters per second. And the acceleration, A of 10, there's nothing to plug in. It's still just 9.8 meters per second squared. So we're still picking up another 9.8 meters per second every second, which again is why the velocity continues to increase, which is why the position tends to increase rapidly. Now, is this how objects really fall? No. You can neglect air resistance up to a certain amount of time, and this model for a well-flowing object, one that's not like, say, a piece of paper and dropping that would be a terrible idea, or something that's just built really oddly and is going to have weird air resistance packets as it falls and rotates. The dynamics of falling objects is extremely complex, but as long as we only look at it for a few seconds, we can neglect air resistance and say, ignore the complexity. So 1 second, 3 second, maybe even 5 seconds in, this is pretty good. This model is kind of past its point of return in 10 seconds, but that's not to say I couldn't just do this on a test or a homework. I can certainly still ask this because I've said to ignore air resistance. But again, eventually with real objects in the real world with oxygen surrounding us, they eventually stop. Otherwise, let's just say you were skydiving, if your acceleration didn't stop, then your normal fall time of say 2 minutes would end up being like, I don't know, 45 seconds, maybe 30 seconds. And you would end up falling so fast that you wouldn't even be able to control your arms and limbs to pull your parachute. And that would happen like 15 seconds in. But I want to say that the average person skydiving falls at about 100 miles an hour, give or take 20, between 80 and 120, something like that. And that's for someone in a normal skydiving positions with their arms kind of and legs wide out. Not one of those, it's an action movie and we're all tucked in to dive really quick to save someone's life or something silly. Because your form changes your air resistance. Some fascinating dynamics. And I wish we had a calculus class that I could teach that stuff in all semester, but it's a little advanced to go into. So that is our objects in motion. You've got your position, your velocity, and the acceleration functions. How do you find acceleration? Take the derivative of velocity. How do you find velocity? Take the derivative of position. In that regard, acceleration can be regarded as the second derivative of position. Now, what's fun is it's actually more common to know the acceleration of an object and try and find the velocity and the position. And you might go, well, how would we do that? If we know the acceleration, which is a second derivative, how do we get to the first derivative? And then if we know the first derivative, how do we get to the regular function? Well, just like there are predictable patterns and formulas to go from a function to its derivative, there are predictable patterns and functions and formulas to go from a derivative to a function. And we're not going to do that for a while, but that is the other main topic of this course. There are 3 topics in calculus: limits, which we've already completely covered, derivatives, which we're going to spend a long time on, and then something known as antiderivatives, which would be the opposite of a derivative, which means you got a derivative and you're trying to find the regular function, also known as integrals. So 3 things we study in here: limits, derivatives, and integrals. That's calculus. But we got a long way to go before we get to integrals, before we get to these antiderivatives. Okay. So with that being said, that is the end of chapter 1.
Sorry, I just had to move something around a little bit. So like I just said, that's the end of chapter 1. And here we're going to get into 2.2. And remember that the chapter 1 material is what's going to be tested on when you take your test next week on your own time.
2.2. Derivatives. Exponential. Specifically with a base of e. Functions. Self lots of space. Okay. Derivatives of exponential functions. Well, remind ourselves what an exponential function is versus a polynomial. Polynomial is something like x to the third, whereas an exponential is something like 3 to the x. Polynomials can have multiple terms, exponentials can have multiple terms. The point is, a polynomial has a constant in the exponent, whereas exponentials have a variable in the exponents. Someone just asked about showing work for the test. Yes, I'm going to get into that next class. So I want to pause on that one. But with the MyMathLab test, I would love for people to show their work. And I will be providing a way for you to submit your work, to take pictures of it or scan it and email me PDFs or image files, whatever, anything pretty much. So that is a great point that I was going to get to next class. Cool. Okay, so polynomials, they have constants in the exponents. Exponentials have variables in the exponents. And we in pre-calc talk about how these things grow really, really fast. We talk about what their graphs look like. If the base is bigger than 1. What the heck was that? I don't know how that even happened. So we said that if your base is bigger than 1, your basic exponential graph does this. This height would be 1. So this is a b to the x, where b is bigger than 1. And then if your base is less than 1, it instead does quite the opposite. It's a horizontal reflection. It reflects the left and the right. So this is when you have b to the x, where your base is between 0 and 1. The left one we call exponential growth. The right one we call exponential decay. We like our money to have exponential growth when we're investing it. That virus, especially in the beginning, seemed to have exponential growth. So money, good, virus, bad. Decay, when we talk about things dying and just being in the ground, they have so many carbon and other types of atoms in them, and they disappear in a predictable way, this exponential decay. So the amount of carbon left in, say, a living or previously living object, whether it's plant, human being, animal, anything like that, we can date how long ago, within reason, that thing died or went in the ground or whatever it was because of these predictable patterns. If you had a population of people that could just grow and grow and grow forever without limits, without any worry about food or space or money or anything like that, our population would be growing exponentially forever. But when you start throwing in more complicated, realistic issues like, oh, we can't fit so many people on Earth. Oh, we can't grow so much food. Oh, we're going to pollute this planet to death if we don't start focusing on saving it, things like that. Then that's what causes those limiting factors with the logistical curves, which again are going to be avoided for now. So just a quick reminder, an example of what this left one could be, this could be 2 to the x, and the right one, this could be 1/2 to the x. Or the left one could be 3 to the x, or 9 to the x, or 2 million to the x. The right one could be 1/4 to the x, or 0.35 to the x, or 0.0001 to the x. Now, we're going to focus not on all of the different types of exponentials. We will focus on having a base of e. That is the critical component. So we focus on having a base of e only. So things like e to the x, or e to the 5x, or e to the 7x squared minus 3x plus 5, or you can have coefficients in front of these. 17 e to the, 31x minus 10. These are the type of exponential functions we'll be looking at. We will only study bases of e because the calculus is simpler with them. It's a simpler formula, and quite honestly, there is a way to turn every single exponential function into one that has e. So if you wanted to use a model of, say, 2 to the x or 9 to the x, there's a way to turn that into e to the x. We don't have to focus on that in this course, but there is a way. That's all that matters. All right, rants aside, quick reviews aside. Now, I'm going to point out that you must know the basic properties of exponentials before we get to the calculus. This is review material. I'm going to write it really quick. I'm not going to do any examples, but things like the fact that, ooh, that was a weird noise my dog made. E to the 0 is equal to 1, or e to the 1 is equal to e. And in the next section, when we're going to get into the logarithms, we're going to need to know, in the next section, we'll need to know that the natural log of e is equal to 1, or that the natural log of 1 is equal to 0, or the natural log of e to the x is equal to x, or e to the natural log of x is equal to x. These properties must be known. This is review material. What was that, R6, I want to say where that was? I'm flipping to my textbook. It's either R7 or R6. Yeah, R6. So if you are rusty with that stuff, go back to R6. I wish this was a calculus class where it's 5 credits and I can do all the reviewing again, but it is what it is. That's all it is. All right, so on to the calculus, on to the formulas. To take derivative of an exponential function. So, in other words, if your f of x is equal to e to the x, now this is the most insane formula you will ever see in your life. I need everybody to take a deep breath real quick, okay? In, out. Okay, f prime of x is e to the x. That's it. I was being ironic. I'm sorry, I'm terrible. The derivative of an exponential function is an exponential function. The derivative of the most basic exponential function is literally itself. Now, if there were coefficients, the coefficient would still be there. Now, this is just the basic concept. We can still throw product and quotient rules in. We can still throw chain rules in, and we will do the chain rule so much with this that we'll actually just give it its own formula, in fact. So in other words, i.e. d dx of e to the x is equal to e to the x. The derivative of the basic exponential function is itself. It is the easiest derivative to do. Don't you wish this was on the first test? Don't worry, just because it starts out easy doesn't mean we can't make it hard. So for example 1, let's find, is that underline still on? Find f prime of x, find the first derivative, given the original function. We're finding f prime of x, or df dx, however you like to write it. So f of x is going to be 5 e to the x. I'm not going to do any examples where it's just e to the x because that example would literally be the definition. I got to throw other things in there. Okay, so let's do it in red. F prime of x. Well, the 5 is a coefficient, so we leave it there. The derivative of this e to the x is quite literally e to the x. That's what it says above. So the derivative is 5 times e to the x. You might think that feels like a power rule. I would disagree. Power rule says we bring an exponent down and decrease it by 1. I didn't bring an exponent down. I didn't decrease anything by 1. That's just it. Or you can write df dx equals 5 e to the x. Or you can be super lazy and just write f prime equals 5 e to the x. All of those are the same. B, let's do f of x equals x times e to the x. Now, x doesn't count as a coefficient. You can think of it that way, but it's a variable coefficient. This is not just leave the coefficient alone, because this is a variable times another thing with variables. Here you're going to need what? The product rule. And since I haven't written it today, I'll write it. D dx. And let's actually use first and second instead of f and g, just to keep mixing up how we write these. And like I said, this is the one that you can mix up all sorts of craziness in terms of consistencies, as long as one of these things has a derivative and the other non-derivative. Because of the plus sign, you can mix and match quite a bit. But I said I like to write out my product rule like my quotient rule, which was going back, going back, going back. Where did I write it? Here it is. So the quotient rule, I like to do second, then derivative of the first, and then swap the order. Second, derivative of the first. So I'm going to be the consistent here. So I'm going to go second times the derivative of the first plus the first times the derivative of the second. Again, I can swap so many different things in regards to this rule. It's insane. So that says f prime of x equals, if you want to write out what your first, actually, hold on, let me pause that. Don't do that part yet. You can, but I like being thorough. Let's say what first and second are. The first is the x. The second is the e to the x. The derivative of the first would be 1. The derivative of x, that's that special case of the power rule, is 1. The derivative of the second, that's quite literally the exponential rule. The derivative of e to the x is e to the x. This only works if the base is e. If the base is 2, it's a crazier formula. If the base is 9, it's a crazier formula. If the base is a half, it's a crazier formula. It's not a crazy formula, but it's definitely wilder. It's crazier. So f prime of x, just make sure you're mixing and matching, doing a first times the derivative of the second and a second times the derivative of the first. Add in whatever order you like, write the products in whatever order you like. I just in particular like this order, so I'm going to be consistent. The second, that's this e to the x, times the derivative of the first. So we're multiplying these two. The derivative of the first is 1, then a plus. Then we do the first times the derivative of the second. We're doing these two, x times e to the x. The first is x. The derivative of the second was literally the same as the first by coincidence. And that's what we get. We don't really need to write something times 1, so that's just e to the x. Then a plus, x times e to the x. There's nothing you can do there. This is the answer. Those are not like terms. They both have an e to the x, but this one has an x and this one doesn't. If this x was not here, if this was not here, you could combine them and say that's 2 e to the x. If this was the case, it would be 2 e to the x, but it's not. So I'm going to undo all that. These are not like terms. You can't combine them. But you could take a GCF out if you wanted to of e to the x. And this is a pretty common technique. It's not mandatory, but it's common. So if I take an e to the x out, then open a parentheses, when we take it away from this term, we're taking the entire term, but because it's got to be a product, that means we're left with a 1. If you distribute e to the x times 1, you get e to the x, then plus. If you take the e to the x away, you're left with the x. Both of these are acceptable answers in my book, and my math lab should count both of them unless they say, write your answer in a factored form. There are times when the first one's better, there are times when the second one is better. That's the thing in math. There is no way to say, in general, this format is always better. There's exceptions to any rule. C. Now this one right here is going to lead to something very important, and that's going to be e to the 5x. Notice the difference between A and C. It is critical. Critical. Critical, critical, critical. In A, the 5 was a coefficient. It pretty much did nothing to the calculus. We just drug it along. In C, this 5 is up here in the top, which means that this part right here is kind of like an inside with other stuff going on, and then the whole thing is like an outside. Guess what? We need to chain that. We need the chain rule, which says that the derivative of an inside and an outside was the derivative of the outside times the derivative of the inside. And yeah, you can write that as f of u times u prime. You can write it as f of x times x prime. There's a lot of different ways to write this. I'm just trying to be the most, I think the best way to say it. And if you need to see the other versions of it not written that way, go to the previous lecture when we discussed the chain rule. But that's how I like to label things, in and out. So for this problem, the inside would have to be the 5x. See, the derivative, where is it? It's right here. If your function is e to the x, the derivative is e to the x. That only applies if the exponent is just an x and if the base is just an e. This exponent is more complicated, so we have to use that kind of substitution technique. So the inside is 5x, making the outside equal to e to the x. And this is when I like to use a different color, where please note that x really, that blue x really represents 5x. It really represents the inside. This is the strength of using the u notation instead, which I was doing at the end. If you said that the inside is 5x, or you could say u equals 5x, and that the outside, f of u, is e to the u. That's the other way of writing this. I do not care which way you're writing things. I care that you have a way that works. That star is in a bad place, isn't it? That also is a terrible looking U. Looks like a 4. U, there we go. So this right here is just the other way. Instead of saying inside and outside, you say U equals what I said is the inside, and then f of u equals, then you just write the outside function with the u replacing it. So our derivatives, the derivative of the inside, the derivative of 5x is 5, so that's a special case. The derivative of the outside, well, the derivative of e to the x is e to the x, but remember that's a special x, it's really 5x. So f prime of x is equal to its derivative of the outside times the derivative of the inside. If you want to do the derivative of the inside first, then the derivative of the outside, that's fine. And in fact, for these, I typically do it that way. I do the derivative of the inside first, but I'll skip it for this time. So the derivative of the outside, that was this e to the blue x. But I don't write x here. I have to write, when we're talking about the outer function, what that's really representing. It's representing the u, which is 5x, or the inside, which is 5x. So again, this right here is this here, but I don't write the substituted variable. I write what was originally the inside. Times the derivative of the inside, well, that was the 5. But we don't like constants being at the end, so we just reorder this as 5 times e to the 5x. That is our derivative. Now, I could do 3 or 4 or 5 or 20 more of these, and hopefully everyone would eventually pick up on the pattern. What happened? So instead of that, let's just try and look at this basic one and see what we get. When I labeled what the inside was the exponent. This was specifically the exponent. And this part right here was just the derivative of the exponent. The e to the 5x, this part right here, was the original function. So when we took a derivative of this exponential with something hairier going on in the exponent, it basically just ended up being take the derivative of the exponent times leave the original function alone. So we're going to make a formula for that so we don't have to practice this chain rule 50 million times. So I don't want to write that. Let's type it. Let's make a rule for chaining an exponential to the base of e. So d dx in black, the derivative of some exponential with a base of e where the exponent is not just x, it's a function. It's 5x or x squared plus 3 or anything. So no matter what the exponent is, this derivative is always the derivative of the exponent times the original function. That's what that says. So I'll put it below. The derivative, we should stop doing that, of an exponential, a more complex exponent, is simply the derivative of the exponent times the original function. That's what that formula says in plain English. If you need to take the derivative of an exponential base e, take the derivative of the exponent, then multiply it by the original function. It's generally not too bad. It's a lot less annoying than having to write out the chain rule inside, outside, inside derivative, outside derivative every single time, or u equals this, f of u equals this, and then showing the work. This is just a quicker setup. Do you have to use it? No. Feel free to show all that chain rule labeling, whichever version you do. But moving forward, this is how I will do every single derivative of that format. So our example 2, which we will find prime of x, or we could just say find the derivative of x, whichever way you like to say that. For A, we're going to have f of x equals e to the negative x squared. This is one of my favorite functions to talk about in calculus. And I don't even want to say why yet. I'll hint at it, but remember earlier I said we're going to learn how to go backwards on these derivatives. We're going to learn how to have a derivative and find what the original function would have been. You can't always do that. And this is one of them that you can't always do that with, analytically, using techniques that we know. But we know how to take a derivative. That's the good thing. All I'm asking for you to do is take its derivative. I wouldn't ask you the other thing. So f prime of x. The exponent is more complicated. It's negative x squared. So we're going to need to take its derivative. Let me leave the formula up there. So because this is of that type of format, e to something else, not just an x. F prime of x, we're going to take the derivative of the exponent. So we're going to take the derivative of this, which is drag the 2 out front and then decrease the exponent by 1. So that's negative 2x. That is the derivative of the exponent, but we don't put that in an exponent. It goes out in front. Then times, so again, that's this part. All I've done so far is that part. Then times the original function. Well, the original function is e to the negative x squared, so times e to the negative x squared. I don't really need that dot there. So f prime of x is negative 2x times e to the negative x squared. Or df dx, however you want to write it. That negative x squared is in kind of a funky place. Let me just make that look a little better. Again, this first bit, the negative 2x, was the derivative of the exponent. That's what this says. Derivative of the exponent times original function. Original function. I didn't change anything. I didn't decrease the exponent by 1 there. Wouldn't even make sense because it'd be x squared minus 1. It would make it look even worse. Not saying that's not possible, but it ain't what's happening. Let's do another. F of x equals 6 times, and we will say this is our last example for the day. F of x equals 6 times, no parentheses, sorry about that, e to the 4x squared, that's a 4, plus 2x. And all of that's in the exponent. So we have an exponential, base e. So the derivative is basically just this thing, but that chain rule says you got to take the derivative of the exponent and slap it up front. So f prime of x equals, leave the 6 there, times. We got to take the derivative of the exponent. Now that's just a straight up power rule. It's a little more complicated than the last one, but it's still just a straight up power rule. So the derivative of 4x squared, you'll bring the 2 out front. And because of that being multiple terms, I'm going to need a parentheses. And you get 8x. Again, the derivative of 4x squared is 8x. Then plus, the derivative of 2x is just 2. That's one of the special cases. That's this right here, the derivative of the exponent. The exponent's what we're calling f prime. And I'm calling the original function f prime here, which is why I'm not calling the exponent f prime in the example. You're saying here's the original exponent, here is its derivative. Too far. Erase, let me erase that circle, there we go. Then times the original function. Now the 6 I already put up front, don't put it again. So I'm just talking about this. That's the original primary part of the function. So times e to the 4x squared plus 2x. Now there's a couple different things you could do. You could distribute the 6 to get 48x plus 12 times the e to the 4x squared plus 2x. That's distributing the 6. Or you can factor, and it's actually best to do it after the distribution because there is a factor of 2 in here. If you pop that out, you get a 12. Or you can say, hey, there's a common factor of 12 inside. Take that out, and you get 4x plus 1 in the parentheses, then the e to the 4x squared plus 2x. Or if you want to make this the ugliest version, this is my least favorite, you could distribute the e to whatever term to the first bit. And again, this is the ugliest one, 48x e to the 4x squared plus 2x, then plus 12 e to the 4x squared plus 12x. All three of those are the same analytically, but I'm going to box up what my favorite 2 are. I'd go with this one, or really the second one is the best in my opinion. But there's nothing wrong with the last one. It is okay. I just think that it's a lot less writing having to write the e to the blah, blah, blah part only once instead of twice. So that's convenient for me. Okay. We'll still do maybe one more example with this next time. Doing some actual evaluations of functions, and then we'll go into 2.3, but for now we'll call it a day.
Not quite a day for us yet. Give me one more minute and we'll get the last video for about another 25 minutes worth of class. And here we go.
And we're going to find f prime of 7 if f of x is equal to x times e to the x. So we did a decent amount of experimentation with these exponential rules, and we said that the derivative of e to the x is e to the x, but that is an extremely rare question to be asked. Usually there's other numbers and variables littered all over that because that's just too simple. So we did this with a constant coefficient. It didn't really complicate things. We did one where there was a product, and we got this, and we did one where there was did we do a quotient? We did not do a quotient, but we could have certainly done a quotient. And then we did something that involved the chain rule. And we said that the chain rule one has seen so much that we might as well just go ahead and derive a formula for it, which was this, that the derivative of some e to a whatever the exponent is the derivative of the exponent, aka the derivative of the inside, times the derivative of the outside, the derivative of the e part, which is really just itself. So the derivative of an exponential with a more complicated exponent, as long as the base is e, is the derivative of the exponent times the original function. It's just the original function with an extra product, that extra product being the derivative of the exponent. Did a couple examples, now let's do a third. Well, I scrolled up intentionally. Just look at this function, f of x equals x times e to the x. That seems, oops, too far. That seems really familiar. So example 1b, we already did this. So we know that the derivative is, and you can use either version you like, it doesn't technically matter. I like the one with e to the x factor. Again, if you have all the terms having the same exponential piece, it is generally better to factor that out. Notice I said generally, not always, generally. So I'm going to use this version of the derivative. I'm not going to reinvent the wheel. I'm not going to do this work a second time. It's already been done. So by example 1, was it B? Ooh, excuse me, that was a rough cough. Yes, f prime of x was equal to e to the x parentheses 1 plus x, right? E to the x parentheses 1 plus x. You could swap the order of the x and the 1. That would be fine. You could use the version where the e to the x was distributed. It doesn't matter. You can redo this whole work if you feel like you need to practice on the product rule. But I need to save some time. So all we gotta do is plug the 7 in. So f prime of 7 is equal to e to the 7 times 1 plus 7, which is e to the 7 times 8, or 8 e to the 7, more appropriately written. Now that is the analytic answer. There is nothing wrong with that. But a lot of people are curious as to what this is approximately. So if you type this in a calculator and round to the nearest whole, 8, second, e with an exponent, 7, close your parentheses, and you get 8773 rounded to the nearest whole. That's the approximation. Please pay attention to my math lab if it wants an exact or an approximate answer. The exact one is what I have boxed up. I'm not even going to box up the 8773. The only reason I would ever care about the 8773 is if this is an application and you wanted a sense of scale to the value. But as a math problem, the 8E7 is more interesting. It's more exact. Okay. What could we do with this? Well, part B, that was supposed to be a part A. Part B, write the equation, you knew where this was going, of a tangent line at x equals 7. 2f of x equals x times e to the x. Well, we have the slope. The 8e to the 7 is the slope. That was the derivative. So by part A, m is the f prime of 7, which was the 8e to the 7. That's the slope. Again, that's the slope. But we need the point. We only have the x value, so we need to find f of x. We need to find f of 7 to get the point. Now we're going back to the original function, not the derivative. F prime and f are different things. So we're just plugging 7s in there, so that will be 7 times e to the 7. So the point is 7 comma 7e to the 7. Lots of 7s. I can't believe I'm going to write this one last time for you. Y minus y1 equals m times x minus x1. There is no reason you should be in calculus if you don't have that memorized. So plug in the point, that was the x1 and the y1. The m was our slope, so we go y minus the y1, which is 7 times e to the 7, is equal to the m, which is 8 e to the 7, parentheses, and then x minus the x1, which is 7. Distribute. You get y minus 7 e to the 7 is equal to 8 e to the 7x minus the 8 times 7 can be multiplied to get 56 e to the 7. And then you can move by adding 7 e to the 7 on both sides. And believe it or not, those are like terms. They have the exact same factor of e to the 7. It's like saying negative 56x plus 7x. Just got to do 56 minus 7, which is 49, but it's negative. So you get y equals 8 e to the 7 power times x. So that's the slope and the x. Then a minus 49 e to the 7. And that is the equation of the line. And you might say that doesn't look like a line because of the e to the 7ths, but those are just numbers. Again, if you wanted to approximate this, we already know that the 8 e to the 7 is about 8773. So the approximation is y equals 8,773x minus, and this 49 e to the 7, so we got 49 times e to the 7. That's about 53,735. 53735. 53735. Again, that's the approximation. Let me use the squiggly equals for that. The approximation is nice because you can see your rate of growth here, the 8773 per year or month or per day or per whatever the x is measured in. You have your y-intercept here, which says you're starting out at negative 54,000 roughly. So if you produce, maybe this is the model for our revenue if we were to produce X items. So if you make 0 items, our revenue is going to be negative 53, or sorry, profit. I don't know why I said revenue, profit. Maybe you'd profit negative $53,735 because you got to pay your rent and employees even though you didn't make anything. So again, lots of ways that we can then make that more relevant to an application. I'm really focusing much more on the math side of things and the applications in this course, given the nature of delivery. I'm not saying we never do applications. I'm just kind of trimming the fat a little bit as I see necessary so that we can finish the semester in a timely manner. All right, so that is going to close out 2.2. So let's make a new, let's go 2.3, which has a different title than what's on my notes. Derivatives of natural logarithmic functions. Derivatives of natural logarithmic functions. Derivatives of natural logarithmic functions. The natural here is extremely important. Not just a derivative of a regular log. This has to be a natural log. So we will not do derivatives of regular logs in this section. There is a section for taking derivatives of non-natural logs and non-natural exponentials. Back in 2.2, all we did was the natural exponential. What that means is the base was e. There are formulas for things where the base isn't e. There are formulas when it's not a natural log. They're more complicated. They're in a later section, and we will cover that if we have time at the end of the semester. Again, I'm going over the things that we need to cover, and then things that are a little more optional I'm saving for the end to kind of circle back to, because I don't think we're going to have time to circle back to too much. We're already a little behind where I'd like to be as it stands, and I don't think that that's going to get any better. But it is what it is. You'll learn enough to have mastered what you need to master. I can guarantee that. Okay. So once again, in the interest of applied calculus, in the interest of not showing you derivations of calculus formulas because it's nightmare fuel most of the time, we're just going to go straight to brass tacks. The derivative, I don't know why I need that in blue. I'd rather have it in red. The derivative of the natural log of x. That's natural log, ln log natural. But we speak English, so we say natural log because we put adjectives before instead of after. But guess what? English-speaking people did not invent this, so it's log natural. So the derivative of a log natural or of a natural log, which just means its base is e. I'll remind us of that in a minute in writing if you have forgotten that. This derivative is 1 over x. So this is a formula that you must memorize. As I said, calculus is basically a series of memorizing formulas and having mastered pre-calculus material, which means having mastered all the algebra that calculus requires to do. Calculus is a series of formulas and applying them. But in the applications, there's heavy, 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 heavy algebra. So as a reminder, oh, and I forgot to do this. All the little things you got to do. ln of x is a log with a base of e. So ln of x would be the same thing as if I wrote this, log base e of x. Don't ever write things this way. It is technically correct, but you are going to annoy some people a lot by writing log base e of x. Kind of like when you write a coefficient of 1, you're going to annoy someone. When you write an exponent of 1, you're going to annoy someone. It's writing extra things. Why do you want to write log base e when you can just write ln? Also remember that if you have log of x, we assume that the base is 10. Again, you would never write things log base 10, you just write log of x. We're not going to be dealing with this type of logarithm in here unless we get to those extra sections later. We really don't deal with regular logarithms. And the convenience is, and I mentioned this for the exponentials, all exponentials can be kind of massaged into a form of having a base of e. You can take something that had a base of 10 and write it with a base of e, or a base of 7 and write it as a base of e. Same thing with natural logs. You can take a natural log of any base and turn it into another base using the change of base formula back from pre-calc 1. But we're going to practice the calculus of things. This is not pre-calc 1. We've done that stuff already. You should have done that stuff already. So, calculus. Example 1. Find f prime of x or y prime given f of x or y. Let's have f of x be 5 times the natural log of x. Okay, so the formula, again, is right here. Got to have it memorized. This just has a coefficient in front of the thing we're taking a derivative of that we just discussed. So coefficients don't really have an effect on it. You're just going to put the 5 in front of your answer. So f prime of x, leave the 5 alone. Then the derivative of the natural log of x is 1 over x. So that's 5 times 1 over x. But no one's going to leave things as 5 times 1 over x. You're going to multiply the 5 and the 1 because they both count as tops. So that's our derivative. The 5 and the x did not multiply. The 5 and the 1 are in tops. Remember, if you need to write this as 5 over 1, you can, but most people generally don't do that. B. F of x equals x squared times the natural log of x. Well, in A, we had the 5 times the thing. Now we've got x squared times the thing. We know the derivative of the thing, it's 1 over x. Now when it was just a constant coefficient, that doesn't have an effect. This is not a constant coefficient. This is a variable, if you will, coefficient. Product rule is necessary. Which, just using my first and seconds, I will write out again as the second times the derivative of the first plus the first times the derivative of the second. There's lots of versions of that. You know, I've said that 50 times by now. You better master it by test 1. And actually, before I go writing all that, let's write what first and second are. So what's the first thing? That's the x squared. What's the second thing? That's the natural log of the x. What's the derivative of the first thing? That's a power rule. Bring the 2 out front, decrease the exponent by 1. So 2x. What's the derivative of the second thing? We were literally just told it's 1 over x. Leap of faith, I know, but take the leap with me, please. It is 1 over x. And there's some fascinating details about that derivative that aren't necessarily true. And when you go with that backwards thing I've kind of talked about, you end up needing kind of more detail in here. The only thing I want to point out that's weird about this is that the natural log function is only defined for positive x values, but its derivative is defined for all values. So this is a slight misnomer. You have to have x being positive. So what some people like to do is then say, come back here and say, note, x has to be bigger than 0. Because you can't take the natural log of a non-positive, you have to restrict the x and the derivative to be the same. You can't let the x be negative in its derivative when it wasn't allowed in the main function. If there's a portion of the domain that doesn't work for the regular function, it's not going to work in the derivative either. Now, we don't get super analytical in this course, so it's not as big of a deal, but I do like to at least point out that you're only supposed to be dealing with positive x's for this statement to be exactly accurate. Okay, back to the problem at hand. We have our product, so we labeled a first and a second. We took each of those derivatives independently. Now we can say that f prime of x. And again, with the product rule, just make sure you're taking a regular thing times a derivative. You're mixing your first and your seconds and you're adding. But again, I like this pattern because it's consistent with the quotient rule in terms of the order that the derivative of the first is in the first spot, the derivative of the second is in the second spot. All right, so second times derivative of the first. That's these two. So the second is the natural log of x times, there's our 2x. Now you got to be careful here. Don't multiply the x and the 2x. The x is inside a natural log, the 2x is not. You can't multiply them. What some people like to do is go back and wrap the natural log in parentheses to emphasize that, in fact. Again, you cannot multiply the x and the 2x because they're in and out. It's kind of like if you have a square root of x times an x. You have an x outside and an x inside. They can't communicate. So now we're doing the first times the derivative of the second. That's this pair. That's the x squared and the 1 over x. So that's plus 1 over x squared. There's our first times, excuse me, not 1 over x squared. I'm reading and writing at the same time. The first is x squared times the derivative of the second is 1 over x. So because it can lead to confusion writing things this way without the parentheses, it is really best to ultimately put that 2x in front of the natural log. That's the better way to write that first term. Then plus, you have an x squared in a top, an x in a bottom. You're going to lose an x from top and bottom. If you had 2 of them in the top, that's going to go down to 1. If you had 1 in the bottom, that goes down to nothing. So again, that's x squared over x. You cancel the 1 in the bottom. The 2 becomes a 1 in the top. That's x to the first over 1, which is just x. So this is our derivative. C. Let's have y equals, let's change up our notation, to the natural log of 5x. I like to do my notes in kind of a specific way that there's patterns. When we were doing the exponential section, we did a 5 e to the x, then we did an e to the 5x, and we saw with the 5 e to the x, that coefficient did nothing really, just got brought along. But when you had the 5 inside, it was a chain rule. Guess what I'm trying to emphasize between A and C here? The 5 outside really did nothing, so it just ended up multiplying by the derivative of the more important chunk. Whereas here, that 5 is inside, so guess what? We need the chain rule. Spoiler alerts, this gets used so much that we're going to go ahead and write a second logarithm definition for a derivative for the chain rule so you don't have to think about the chain rule every time. But before we get that far, all right, so we need to label an inside and an outside. Well, the inside would be the 5x. The outside would be the natural log of, and again, I like emphasis here. This isn't really an x. This x is that u. It represents the inside. So please note that the blue x is really the original inside. So remember, the chain rule says f prime of x would be the derivative of the inside times the derivative of the outside. Derivative of the inside times the derivative of the outside. So we need to take these derivatives. The derivative of the inside is 5, because that's a linear term. That's one of the special cases. The derivative of the outside, well, the derivative of the natural log of x is 1 over x, but that x is special, so it's 1 over what really means the inside. So y prime, because this wasn't an f, it was a y, or you could write dy over dx. It's going to be the derivative of the inside, which is the 5, times the derivative of the outside, which is the 1 over x. But it's that 1 over the special x, which you may write as a u if you prefer. That represents what the inside is. So this blue x, I don't write x, I write 5x. Because again, this right here is the same thing as this. Well, here's what's interesting with this problem. There's a 5 in the top and a 5 on the bottom. The 5s cancel. And we get that the derivative is 1 over x. Huh, interesting. It's the same as without the 5. Now, I will point out something critical. This is not always the case. It depends on the complexity of the function. It depends on the complexity of the function. Back in pre-calculus, we saw some functions that their inverses were the original function, and that was kind of fascinating. And in fact, 1 over x is one of those. Now, what we're doing here has nothing to do with inverse functions, but what I think is fascinating is that the derivative of the natural log of 5x is the same as the derivative of 5 times the natural log of x. What's interesting here is a coefficient inside of a logarithm does not affect the rate of change. Rate of change means growth. It means its slope. I'm just saying this is interesting because when we had the 5 outside, it did affect its rate of change. The derivative was 5 over x instead of 1 over x. It's growing 5 times as fast. If I put a 7 here, it would be growing at the same rate. If I put a million here, the natural log of a million x, it would be growing at the exact same rate as if I just had a natural log of x. Now, if there's other variables in there, if there's an x squared or a 7x or an x to the 5th or anything like that, that's much more complicated and it does affect the change. But a constant inside of a natural logarithm doesn't actually affect the rate of change. It doesn't affect the slope.
So on that bombshell and with perfect timing, that will be it for the day. We'll pick up in 2.3 when we come back next time in a week. For now, you know your due dates, 1.6 due today, 1.7 and 8 due next week. Test 1 on your own time, available the 21st through the 23rd, due by basically midnight the 23rd. Make sure you show your work. Make sure you submit that in Canvas. That's also how you'll get partial credit. I think I forgot to talk about that, but you can email me and say, hey, Mr. Beckner, I think I need partial credit on number 2, 3, and 7, and I can go look at it and maybe give you some partial credit because my math lab's not going to do it initially. Besides that, if you have any questions, as always, you can email me. Start studying. Don't forget the review is in the homework section immediately under the 1.8 homework. Well, I say homework section, the assignments section. The test, when it becomes available, will be at the very top of your assignments. Shouldn't be too hard to find. Besides that one, have a good night. Take care. Have a good weekend, and we will see you in a week.